Section 2.2 is all about sets. A set is a collection of related objects called elements. And when you see this notation, you can read it one of three ways. You can say X is a member of S. You can say X is an element of S. Or you can simply say X is in S. And sometimes we choose to represent sets pictorially. So you can choose any shape you like to represent the set. Here I've chosen a circle. And then you place the elements inside of the set. So I've placed here the element X in the set S. To say that a set S consists of elements x1, x2 through x sub n, we write the following. Using this notation, the curly brackets in mathematics represent set brackets. So we say S is equal to, using the set brackets, just a comma-separated list of those n elements. So x1, comma, x2, comma, all the way up through x sub n. It does not matter what order the elements are placed inside of the set, just what the elements are. If there is some property P that some elements of S share, then we can describe those elements using set builder notation, which looks like this. We use the set brackets, and we say the elements X in set S, and then this vertical line is read as such that. So the elements X in S such that the elements X have property P. And we call this set builder notation because it allows us to build new sets from existing sets. Let's look at an example. So here we have the set A. It contains the elements 1, 2, 3, 4, 5, 6, 7, and 8. We could say the element 2, or 2 is an element of A. We could say 9 is not an element of A. And we could build a set B using our set builder notation. We could say take the elements X in set A such that X is odd. So we would look at all of the elements of A and just choose the elements that are odd. Those include the numbers 1, 3, 5, and 7. A subset A of a set B is a set that is contained in B. So when you see this notation, you can read it one of two ways. You could say set A is a subset of set B, or you could say set A is contained in set B. So to say A is a subset of B is to say if X is an element of A, then X is an element of B. And again, let's look at this picture representation to see if we can make sense of this. When A, set A, is completely contained in set B, if we choose any element, we'll say X in A, that element must also lie in the larger set B. So in symbols, what we're saying here is that to say A is a subset of B is logically equivalent to this implication. If X is in A, then X is in B. So there are some number sets that I want you to be familiar with in this class. So let's just review those so that you can recognize them. We have the set of integers. The integers are represented by this double bar Z. And the integers are all the numbers that you would traditionally use to label a number line. So they span from negative infinity to positive infinity, and they contain numbers like -3, -2, -1, 0, 1, 2, 3, and so on. We have the set of real numbers. The real numbers are represented by this double bar R. And the real numbers are any number that you would deal with in like an algebra class, except for any even root of a negative number. Remember from your previous math courses, when you take the square root of a negative, you get the imaginary number I. So as long as you don't have the even root of a negative number, any other number you can think of is a real number. You have the rational numbers, which are represented by this double bar Q. And we can use set builder notation to talk about the rational numbers. They are literally numbers in the form of a ratio. So they look like A divided by B, such that A and B are both elements of the integers, and B is non-zero because we never want to divide by 0. But any number written in this form is what we call a rational number. And finally, we have the natural numbers. The natural numbers are your counting numbers, so they do not include 0, but if you were to count on your fingers, 1, 2, 3, and so on, those are your natural numbers. They span from 1 to positive infinity. So some examples. Since every integer is a real number, we could say the set of integers is a subset of the set of real numbers. But 1.5 is a real number that is not an integer, so the set of real numbers are not a subset of the integers because the set of real numbers are not completely contained in the set of the integers. The empty set is the set that contains no elements. The notation we use to denote the empty set is a 0 with a slash through it. And the empty set is a subset of any set that you can think of because we can always take the set with nothing in it as a subset of any set. So in symbols that looks like this. The empty set is a subset of the set X for all sets X. The logical connectives and, or, the negation symbol, if then, if and only if, each of those logical connectives has a set theory counterpart. So recall from the previous slide, to say A is a subset of B is logically equivalent to this implication: if X is in A, then X is in B. If we want to talk about the union, A union B of two sets, A and B, that would be the set containing all the elements of both A and B put together. So down here I've represented that A and B are both the circles in red. And if we want to represent the union, we take any element in A and any element in B. So what we're saying here is an element is in the union, A union B, if it is in A or if it is in B. So in symbols, we could write that A union B is equal to X such that X is an element of A or X is an element of B. So for all X, it is logically equivalent to say X is in the union, A union B. That is logically equivalent to saying X is in A or X is in B. The intersection, A intersect B, of two sets A and B is the set of all elements that A and B have in common. So again, with the pictures, the intersection is represented by the intersection of these two circles. It's all of the elements that A and B have in common. So in order for an element to be in the intersection, A intersect B, the element must be in both sets. So in symbols, what we're saying is that A intersect B is equal to X, such that X is in A and X is in B. And we get another logical equivalence. For all x, x is in A intersect B. That statement is logically equivalent to saying x is in A and x is in B. The universal set U is the set of which every set is a subset. This idea is similar to the idea of domain in logic. It tells you where your elements are allowed to be pulled from. So I've represented this pictorially down here. When we're using this Venn diagram to represent sets and their union and intersection, we typically choose to put those circles for the Venn diagram inside of a larger rectangle, and that rectangle represents the universal set. So the complement, we'll call it A prime, of a set A is the set of all elements in the universal set that are not in A. So if we look at our Venn diagram, the set A is represented in white, and we've shaded everything else inside of this rectangle, including the elements of B that are not in A. All of these things in red would be in A complement. So A complement is the set of all elements X in U, the universal set, such that X is not in A. So this is similar to our idea of the negation symbol. All of the elements X in the universe such that X in A is negated. So we say two sets are equal if they have the same elements. So for all X, X is in A if and only if X is in B. So to show two sets are equal, you must show two things. Remember, the implication here can be read in both directions. So we first need to show the implication read from left to right. If X is in A, then X is in B. Recall that's the same thing as showing A is a subset of B. Then we show the implication in the other direction. If X is in B, then X is in A. Again, that would be the same thing as showing B is a subset of A. So our final logical equivalence here, for all X, to say the set A is equal to the set B, that is logically equivalent to saying X is in A if and only if X is in B. So each of our 5 logical connectives have a set theory counterpart. And you can continue on with the slides in video number 2.